Hey everybody, this is lecture 6.2 on double integrals over general regions. In the previous lecture, we learned about double integrals that captured volume under the graph of a multivariable function, or at least for us, a two-variable function f of xy. And in that video, the only examples we did were over rectangular regions where the x and y bounds a, b, c, and d in our iterated integrals were all constants. And it turns out that you can do a lot more general techniques with double integrals. You can compute volumes over different looking regions in the xy plane than just rectangles. And this is fortunate because if we couldn't do that, we would have to approximate using the infinite summation and limit process we learned last time, and that's a pain. So what we're going to do in this video is do the same sort of double integral computation, hold one variable constant and integrate with respect to the other, doing things one at a time. But we'll learn how to set up double integrals over general regions. So that's the first goal. We'll also understand and practice carefully how to evaluate these integrals. And that's really the sometimes confusing part when you first learn this, how to evaluate an integral where the integral bounds on the inner integral contain variables. And finally, we'll learn to recognize when to switch dy and dx and integrate in a different order. There's not a hard and fast rule for this, but in general, you're able to switch because of Fubini's theorem from last time. And this gives us an extra technique we can use on double integrals that we didn't have for single integrals. All right, so to warm up and to really do our first practice problem that's not a rectangular area in the xy plane, let's take D to be the region shown on the left picture, the triangle with these three vertices in the xy plane. And let's try to compute a double integral over this region of the multivariable function 4 times x times y. There's a three-dimensional rendering of this shown on the bottom right. And you can see that there is a volume to this shape. The blue surface is z equals 4 times x times y. And then the base in the xy plane is this gray shaded triangular region. And what we learned last time to compute an iterated integral is to, if we fix one of the variables, let's say x, and slide in that direction, then for every given x input, sliding in the y direction afterwards will give us a small cross section of the surface or of the three-dimensional region, and we can take the area of that gold cross section and integrate to add up all of those cross-sectional areas. This should be reminiscent of the cross-sectional area approach that we took early in the course, but now we're using double integrals to do the computations rather than integrating some area formula. So what we're going to do is learn how to parameterize or write down equations describing this xy plane triangular region and use that to put into the bounds a, b, c, and d of our double integral to get an iterated integral that we can solve. So I'll do this one with you. I'll actually do every example with you in this video, but I'll leave some parts for you to do at home, as always. So here's the problem again. We want to compute this double integral over this triangular region. And the key here is, first of all, to decide if we're going to do a dx or dy integral first. And remember that the one we do first will go on the inside of the iterated integral symbol. I'll write that out in a moment. But let's, for the purposes of this problem, decide together to integrate dy first. Or on the other hand, you can choose which thing you want to integrate second. And for me, because things are oriented the way we usually think of it, where x is an input variable and y is an output variable, even though they're both independent variables in the setup, I'm going to try to describe the sides of this triangle and the region that's captured by these three vertices using functions y equals some function of x. So the first step, the easy part, is figure out what the total range of x values are that describe this region. And if I'm only allowed to choose x ranges, I see that I'm allowed to range from 0 up to 4. All right, I'm actually going to write it carefully like this: x equals 0 to x equals 4. And now, once we choose the range of x values, we have to describe the y values that will capture only the stuff in the gray region. Notice that if I said, and it goes up to y equals 2 here. Notice that if I had said y equals 0 to y equals 2, this would be a rectangle, and somehow that's not capturing the triangular shape that we need. So instead, we ask the question, for a given x input, between 0 and 4, how does y vary at that single slice at x equals, it looks like 2.5 in this example. So for that given x input, the y range is determined by this function. You can think of this as the top function in our area between two curves section a long time ago. And this top function is described by a linear equation. Let's see, it's y equals 1/2 x. I believe you should check with point slope form or something, but yeah, it's y equals 1/2 using rise over run. So this tells us that, well, the lowest that the y values can be is always 0. That's the x axis that's shown. And the highest the values can be are, well, it's a triangle, so it depends on where our x bound or where our x value is chosen to be. But once we choose an x value, then the y values can range all the way up to that line given by y equals 1/2 x. So this is our first example of having functions with variables in the bounds of an integral. Let me show you how to set up the resulting iterated integral. So I'm going to work outside in. We know that we're going to integrate the x variable last, so that goes on the outside, and its bounds are 0 to 4. We're going to integrate the y variable first, and the way that we know this, and this is presumably the first time you're doing any iterated integrals with variables in the bounds, then I'm going to tell you the rule of thumb. If I have y bounds that involve a variable, in this case y equals 1/2 x is a function, that needs to go on the inside. And the other way to remember this, an equivalent way to remember it, is at the end of the problem, when we have only a single variable left to integrate, there cannot be any other variables in the bounds. So the constant numbers 0 and 4 have to go on the outside. So I'm going to write this just shorthand x over 2. The function we're integrating is 4 times x times y. We're integrating dy on the inside and dx on the outside. And let's go ahead and solve this thing and see if we can make sense of this entire expression. So using our integrated integral procedure, I'm going to leave the dx stuff on the outside alone. I'm going to evaluate this integral on the inside. 4 times x times y, where y is the variable, becomes 2x y squared by the power rule. And I'm evaluating this, and I'll carefully write this in to remind you, from y equals 0 to y equals 1/2 x, or x over 2 dx. So let's not worry about the dx stuff on the outside still. Let's just work on evaluating this inner expression by plugging in y equals 1/2 x and y equals 0. This is just the same as our ordinary fundamental theorem of calculus, where you plug in the bounds and subtract the results, except our bounds now involve variables. But that's okay. This is a multivariable function. It's really doing a substitution. So let me still leave the outer stuff alone. On the inside, when I plug in y equals the top bound 1/2 x, I'm going to get, let's see, 1 over 4 times 2 is just 1/2. That'll be x, and then another x squared will give me x cubed. And if I plug in, notice if I plug in y equals 0, that just gives me 0. So here's the integral that we end up with, and I can actually take away the brackets now. Now let's leave them in for spacing. And this is a fairly easy integral to solve. This is really a single variable power rule problem. So later in the video, I'll leave these for you to do, but just so we complete one problem together, let me quickly integrate this. If I raise to the 4th, divide by 4, that'll give me 1/8 x to the 4th, evaluated from 0 to 4. If I plug in 4 raised to the 4th, that's the same as 2 raised to the 8th. And here I have 2 raised to the 3, so I'll be left with 2 raised to the 5, which is 32. Notice if I plug in 0, I get 0. So the result is 32. The volume of this funky, curvy wedge-looking shape is 32 on the nose. And in other problems, we'll certainly get stranger-looking values that aren't just whole numbers. But there we go. Our first iterated integral over a region that's not just a rectangle. And at this point, the rest of the video, we're going to spend learning a couple other tricks for how to deal with this situation. But most of our iterated integral problems will look something like this. You'll either be given a region in words, the triangle with these 3 vertices, or something more complicated, or you'll be given a picture like on the bottom left. And ideally, you have both. So if you're given one, you can draw the other or write down the functions that describe this picture. And that will allow you to set up the double integral. The important part for you to learn in this video and doing practice problems is how to set up the integral and also how to compute the first stage on the inner integral, because that will involve plugging in bounds that have functions with variables. Once you are able to evaluate that part sufficiently, then you'll be left with a single variable integral like we had the 1/2 x cubed in the last problem, and that's just a review problem from Calc 1. So let's keep going. The main takeaways here from this first problem and our general procedure in this video are to find a double integral over a non-rectangular region. We want to first find the x values describing the total spread of the domain, where the domain begins and ends in the x direction. And these numbers will be used as the bounds on the outer integral in the iterated integral. For the inner integral, we need to find functions of the form y equals some function of x that describe the top and the bottom of the domain, and these will become the bounds on the inner integral, and they will in general involve variables. Notice that for part 2, the type of thinking you need to find these functions is exactly the type of thinking that we developed early in the course when we talked about the area between two curves. So given a picture that doesn't necessarily have functions describing it, the same type of procedure can be used to come up with two functions describing the top and the bottom function. And we'll also see, similar to that area between two curves section we studied early on, that there are some difficulties that arise when functions in the xy plane may cross. So we have more complicated regions than triangles, rectangles, and things with a single top and bottom function. And we'll see one of those examples in a moment. By the way, here are all of the rules that we could possibly want to have. Actually, these are not even all of them, but these are a lot of the rules that we have for single variable integrals that also apply to double integrals and higher versions of these. So for example, if I have two functions f and g, both multivariable functions, and I want to integrate their sum f plus g over the same region d, then I can split up the integral into two pieces, one for f, one for g, and calculate accordingly. Similarly, if I multiply by constant, I can pull out that constant. And rule 3 is, if I remind you of a rule from Calc 1 for single variable integrals, rule 3 is pretty familiar as well. So if I have an interval, and I want to integrate over the interval from, let's say, a to b, then if I stop somewhere in between, let's say at point c, then the integral can be split up into an integral from a to c, plus the integral from c to b. And in 2 dimensions, we don't just have intervals to worry about, we have domains, d, and in this case, if d can be written as the union, or the total set of two different non-overlapping sets d1 and d2 in the xy plane, then to compute the double integral over all of d, it's enough to compute the integrals over the smaller pieces and add up the results. And the operative word here is non-overlapping, or in mathematical terms, these are disjoint sets in the xy plane. When this comes up later, I will point out an example of rule 3. But the idea is we can add up volumes by partitioning into separate pieces that don't overlap and computing smaller volumes that way. So here's an example of if this were an area between two curves problem. We actually have 3 curves here, y equals square root of x, y equals 0, and y equals x minus 6. There's a computer-generated graphic for you to stare at for this problem. But if we want to compute the volume using the following double integral of the function x plus y, we need to do a little bit of work to set up our iterated integral. And I'll give you a hint ahead of time. There will actually be 2 different iterated integrals, just like if we computed the area between these, or the area of this gray region here, we'd have to set up 2 single variable differences between 2 curves. So let's try to work some of this one out together. And I already showed you at the bottom of the screen, I'm going to set this up as a sum of 2 different non-overlapping regions. So that's a big hint on this problem. But if we didn't know that going into the problem, how would we try to go about setting up any iterated integral to compute this volume over the region D? Well, we'd first look at the x bounds and say, what's the total spread in the x direction of this region? Well, x certainly starts at 0. And if I look carefully, it looks like it ends at 9. So those are going to be the x bounds on the outside. Here's where things get tricky. The y bounds, so for any given x value, the y bounds are ranging from 0 on the bottom up to the function, which we have a formula for, as long as we're between 0 and 6. However, if I choose an x value here, later in the region between 6 and 9, then the x bound, the y range is much smaller. It starts at the positive sloped line, and it ranges up to the square root function. So because the y value ranges depend on where you are in the x region, I'm actually going to split up my x region into two pieces. And consider these separately. So this is a trick you should use in general. And the basic story is if I can see, and let's do this in a different color to distinguish. If I can see a place where the nature of this region changes, and more specifically where the top and bottom functions change at a certain place in the x bound or in the range of x values, then I need to split up my double integral into two pieces according to where it changes. In this case, I'm going to split up at x equals 6 because to the left of this value, this shape is a single top function and a single bottom function. And to the right of this shape, I have a different, this is really just a triangle. No, sorry, it's not a triangle. The square root function is not a straight line. I have a different shape with a top and a bottom function, but the bottom function changes from the left region to the right region. So if I gave these two names, if I said that this was region D1 and D2, what I'd really have here when I write it out is an integral over D1 plus an integral over D2. And notice that these two regions do not overlap, or they only overlap on that vertical blue line, but that's not going to change the value of the volume. So I'll just remind ourselves that this is the integral for D1. And this is the integral for D2, but I'm going to write it directly as iterated integrals with integral bounds in a moment. And you can jump straight to that in any problem like this. So let's figure out the y bounds in each of the regions. So for the region D1, that's here, when x is between 0 and 6, the lower bound for the y value is 0. It starts on the x-axis, and it ranges up to this square root function here. So the highest the y value can be is square root of x. Again, we're given a formula for that curve up here. And if you didn't know that, you'd have to be told something in the problem to understand it. So these are going to be our y bounds in the first integral for D1. And let's do the second region. When we're between 6 and 9 for the x value, the y ranges start at the line and go up to the curve. We have equations for everything. Here's the line and the curve. We're ranging from 6 equals y equals x minus 6, the line, up to y equals square root of x again. So these are more complicated integral bounds than in the previous problem, but let's plug all of these things in just to set up our sum of two iterated integrals, and from there it's just a process of carefully performing the calculus. So in the first integral for D1, my x values on the outside range from 0 to 6, and my y values range from 0 to square root of x. That's capturing all of this information in a single double integral notation. On the other hand, for the D2 integral, my x values will range from 6 to 9, and the y values range from x minus 6, the line is on the bottom, up to square root of x. Now we're in a position where we can evaluate these double integrals just as we did in the last problem. I'm gonna give myself a lot of space to work here. Let's keep the outer dx part of the integral untouched for the moment, and let's integrate the inner expression with respect to y, since dy appears on the inside. So dy, I have x is a constant, so I acquire an extra y, whereas y by the power rule becomes 1/2 y squared. And then we're going to evaluate this from y equals 0 up to y equals square root of x. So that's our first, the first step of integrating this double integral is just do the dy part, and then we'll need to evaluate these. And we'll still have a dx on the very outside to handle at the end. For the second of these two integrals, I'm going to keep my 6 to 9 untouched on the outside. We need to integrate this expression again, which will be the exact same integral with respect to y. So this is the easy part actually to do the calculus. And then we'll have to carefully evaluate from y equals x minus 6 up to y equals square root of x. We'll keep a dx on the outside because we still have one more integral to do. Now it's just a matter of cranking through this notation. This part can be a little hairy, so I'm going to go slowly through this. And you'll see at the end, I'm going to leave something for you as an exercise to finish, but let's get pretty close to, let's get down to something that we could have solved in Calc 1. So when I plug in y equals square root of x, here I have x times square root of x. I'm going to rewrite that as x to the 3 halves, because in a moment we'll need to, and actually I'll leave it for you to do, you'll need to evaluate this as the integral of x. When I plug in y equals root x into y squared, that just becomes x to the 1. And when I plug in y equals 0, everything becomes 0. So this is actually everything we get in the first integral. In the second integral, we'll eventually integrate from 6 to 9 in the x direction, but I need to plug in the integral bounds here. When I plug in square root of x, I'm actually going to get exactly the same expression. Notice that it's the same integrand and the same top y bound. So look at this expression. However, when we plug in y equals x minus 6 on the bottom, this is giving us a different value. So this is x times x minus 6 plus 1/2 x minus 6 squared. And then there's a dx. Sorry, I ran out of room at the end there. Let's actually clean that up a little bit. Got a little bit of space to shift things over. I'll try to slide everything in there for you. And at this point, these are two single variable integrals. Once I finish writing it, I think I'm probably missing a bracket. There we go. These are two single variable integrals that you can now solve on your own. And I'm going to leave that for you as an exercise. There's a little bit of simplification to do here, but it's nothing too dramatic. A little bit of foiling and maybe combining like powers of x if you want to make it simpler. And then it's just a matter of doing, it looks like every single, once we FOIL things out and distribute, it looks like every single term in both integrals is just some power of x, and then it's a power rule problem. You'll have to evaluate at the end. I will leave that to you to finish computing. And if you want to see the answer, you can find this in the textbook with the numerical answer, but I really encourage you to not look at any solutions before trying that on your own. That's, again, just a single variable integral, but theoretically, these are the things we have to handle to solve these problems. All right, so we practiced with a triangle. We've now practiced with a region that had to be split up into two regions. What else can go wrong? One trick that I want to teach you before, and this one will only really occur in certain circumstances, is what happens when the region that we're integrating over has a particular symmetry to it. So here, if we let D be the region x squared plus y squared is less than or equal to 9, hopefully at this point you recognize this as all of the points on or inside the circle centered at the origin of radius 3, or all of the points distance at most 3 away from the origin. Those are equivalent statements. This region can be split up into the right and left semicircles, or the right and left halves of the region. And the reason that I'm going to treat things that way is, well, if you had a computer system to graph things for you, you'd see that 1/2 of the three-dimensional graph in the positive x direction lies above the xy plane, or has positive height in the z direction. And the other half has negative height or lies below the xy plane. And since our double integrals are computing assigned area, where regions above the xy plane have a positive volume and regions below have a negative volume, we can actually exploit this feature to compute this double integral by relating the value of the volume on the gold half, which will be positive, to the value on the red half, which will be negative. And actually, we'll see in a moment that these cancel out to give you 0. Let's see specifically why this is true by setting up the double integral over this region and exploiting some symmetry of the region and the function. So here's the problem that we're given again. And I'm going to call the right half D1 and the left half D2 so that we can write by that rule number 3 for integral properties a few slides ago, we can write this double integral over all of D as the sum of a double integral over D1 plus a double integral over D2. And this is the point here is that the gold and red, the two semicircles here, do not overlap. Okay. Now, if you had to guess, you'd probably say this is positive because on D1, our X values are positive, and this one's negative because on D2, where the X values are negative, the heights are going to be negative. But if you weren't sure about that, let's just, let's stare at our formula for the function. Actually, I have enough info down here. I can see the function here. What happens as we pass from region D1 to D2? Well, the values we plug into the X part, and notice that the rest of the expression only involves a Y, but in the X part, the only thing that's changing if we flip over the Y axis is that a plus sign becomes a negative sign. And because I'm taking a cube root rather than a square root or something like that, the negative sign will come out to the front. The way that I'm going to write this out for you is as follows. So for the D1 region, this is where X is positive, and it's just the integral of this function. And I'll just keep writing dA because I don't want to have to actually integrate with respect to X or Y to perform this. Although we definitely could, because this is one of those problems where we can separate into a product of two single variable integrals. On the other hand, the second region is where X is negative. We're going to exploit the symmetry now in this step because plugging in negative X values into this function, and again, the Y plus 3 does not depend on X at all, is the same. And let's actually, I'm just going to copy paste the first expression that we won't touch. This is exactly the same thing as plugging in positive X values and adjusting by a minus sign. Sorry, I still need the Y stuff is still in there, although I'm not changing it. And now let's do one more step to simplify. Again, I'm going to copy paste that first integral that we're not changing. And like we said, the minus sign here gets to come out all the way to the front because it's a cube root. So in this case, I'm going to have a minus the double integral for positive X values, or the double integral over D1, if you prefer, of cube root of whatever X values those are, root Y plus 3 dA. And now we see, look, this expression is identical to this expression. So they subtract and we get 0. We want to be careful about subtracting two integrals. We should ask, do these integrals exist, or do they have values? And using terminology from early in the course, are these improper integrals or not? Well, they're proper integrals. They do converge. They do have actual volume numbers attached to them, because theoretically you could write down bounds for these things and compute these regions. You have a continuous function. This is continuous on this domain. A continuous function over a closed and bounded region. So you're able to do a double integral in this case. But because each of these are finite values and we can subtract them and get 0, we'll say that the whole region has signed volume 0. The part above the XY plane cancels out the part below the XY plane. All right, so that's a trick to be aware of if you need to do fast computations of double integrals. We can use symmetry if and the key here is that our region, in this case, the inside of this circle, is symmetric about the y-axis, meaning changing from X to negative X produces a mirror image point on the other side, and we can split up the region into identical pieces where one is being subtracted. Here's a summary of what's going on here using a different type of symmetry in a figure shown in the picture below. But in many instances, if we have a function and a region that are both symmetric, The function being symmetric means that if I switch the sign of the x or the y coordinate, then the function values either stay the same or change by -1. And the region being symmetric means the same sort of thing. If I fold over the region about some line, then I get an identical copy of that region. Then we can exploit this to show that the integral is 0 sometimes. If the region D that we're integrating over is symmetric about some line, this is the same as saying that if we fold the region over L, then one side of the line that we folded over looks identical to the other side that we folded onto. And a function is anti-symmetric. It's just a fancy way of saying it's symmetric, but you pull out a -1, or it's an odd function from single variable calculus. This means that if I fold over a line, then it multiplies the function outputs by -1. This can be done for any lines. This is just a fancy notation for saying fold the x and y inputs over a line. But in practice, we'll just be looking at symmetries about the x or the y axis. So what this would say is that if I plug in -x comma y, that would be symmetry about the y axis like we just saw. This would spit out a minus sign, and that's true of the cube root function. For symmetry about the x-axis, that would say if I plugged in the -y instead of a positive y, so x comma -y, then I can pull out a minus sign. That would be anti-symmetric about one of the two axes. And here's an example where if I have a line running through our symmetric region D, this line could be the x-axis in this case, then folding over and taking this point xy to its partner down below would change the function value by a -1 sign. Then the total double integral over this region would have to be 0 because all of the top values give you a positive or a negative, depending on what the sign is. And then the bottom values give you the opposite sign. So these would cancel out. There's another type of situation that I want to make you aware of, which double integrals are actually really well suited to solve. And if you go back earlier in the course, we were talking about solving different types of integrals using all sorts of techniques. We had substitution, what we call U-sub. We had integration by parts, made a couple other tricks we used. One thing that we mentioned a few times is that integrals of the form e to the x squared, or in this case, for this double integral, e to the y squared, are impossible to solve. And it's a good thing to remember in this course. We've seen this show up in a few different circumstances, that e to the something squared, e to a variable squared, is impossible to integrate by itself. However, the slide indicates that we can probably do something using a double integral to make this a tractable problem. So if we aren't necessarily looking for the area under the curve e to the y squared over a particular region, but instead we look at this as a height function, z equals e to the y squared, where there's no dependence on x, then we can actually integrate this function over different regions in the xy plane, and hopefully we'll be able to obtain some value for this integral. So this is a double integral problem, and I gave you a picture to look at. Let me switch over to the slides and show you the setup. And before even trying to write down an iterated integral, I want you to think about the following question. Is it easier to integrate this function over the region D with respect to y first, where I put dy on the inside, or with respect to x first, where I put a dx on the inside? Pause the video and see if you can identify an answer to this question before we proceed. So once you've stared at this function for a moment, like I just said, it's impossible to integrate with respect to y first because the function is e to the y squared, and we don't know how to integrate that function. Therefore, we're pretty much stuck with integrating this expression, but now this gives us a template. This gives us a strategy to implement on this problem. If we're integrating with respect to x first, then I need to describe the y bounds as constants, because on the outer integral, or the second one we do, we'll have to just have numbers. And the y bounds here, we can see from the picture, range from 0 up to 2. It's just ranging in this direction. And then for any given y, the x range will be described by this function. So let's write that down carefully. The x bounds for this triangle range from x equals 0, that's the y-axis on the left, up to x equals some function of y. And this is a line, and probably your brain works like mine, where we think of this as y equals some function of x. It looks like it's a slope 2 line, so that's going to be y equals 2x running through the origin. And then I can just solve for x and write this as y over 2. So x equals y over 2 describes the line, and this describes the x ranges once we've chosen a y value between 0 and 2. So let's set things up. I have all the information I need now on the screen, and the integral over the region D, that triangle of e to the y squared with respect to area, is given by the iterated integral that we need to set up now. We're going to integrate from 0 to 2 with respect to y at the end, but first we're going to integrate with respect to x from 0 up to y over 2. The function is e to the y squared dx and dy. So I'm just going to scroll down and work this out explicitly. So I'm leaving the 0 to 2 alone. I need to, before applying those integral bounds, I need to integrate e to the y squared. I don't know how to do that with respect to y, but I do know how to integrate this with respect to x. That's just a constant. So I'm just going to get x e to the y squared. And this is really the beauty of this double integral technique. Once we make the substitution x equals 0 to x equals y over 2, this becomes, or this will become in a moment, an actual integral that we can solve using substitution. So let's not get ahead of ourselves and finish evaluating at the x bounds on the inside. If I plug in x equals y over 2, I'm going to get 1/2. I'm just going to move the constant out, 1/2 y e to the y squared. And hopefully at this point you should be cheering, or at least in your head saying, good, that's a relief. I can actually integrate this in a moment. We just added in this y factor just using double integrals that will allow us to solve the impossible e to the y squared using substitution. But also we need to plug in x equals 0. If we do so, we get a 0. So that's the whole integral. Sorry, I messed up. These are dy's on the outside. So can you solve that integral? I think so. I'm going to leave that as an exercise as well. This is a review from U substitution. And theoretically, these are things that you have to do in order to fully solve a double integral problem like this. But the main trick that I wanted to teach you here is looking at the two possible options for order of integration and making an intelligent decision about which option to pursue. In this case, we were forced to choose the dx first, where dx is on the inside, because we don't know how to integrate e to the y squared. But in other types of problems, it might not be as clear. There might be a way to integrate a slightly more complicated function than e to the y squared, but integrating with respect to the other variable first might make your life easier in certain ways. And again, Fubini's theorem tells us that if we're able to do both integrals in either order, then their values have to be the same. So it really gives you two possible routes to success. Let's wrap things up with a couple closing comments. So this is just a recap of what we learned in the last problem. If you don't know the antiderivative of a particular integrand with respect to one variable, then you'll need to switch the order of integration. And the key takeaway is really we need to remember to change the bounds too. If the iterated integral is given to you with bounds already in place, you'll need to draw the region and refigure out the new bounds in the opposite order so that the inner bounds involve functions and the outer bounds are constants with respect to the outer variable. And this is really the thing that can trip people up on most of these problems, especially as you're learning. There's one more application of double integrals that I want to make you aware of. We won't spend a ton of time talking about this, but if you have a region D in the XY plane, there's a theorem, which I'll show you a picture to convince you is pretty believable. There's a theorem that says the area of that region just in the XY plane can be computed by the double integral over the region of the function f equals 1 with respect to area. So we've been doing double integrals where the functions are actual functions of x and y. Here's a constant function. You can think of this as the function z equals 1, meaning whatever in x and y we plug in, the height is equal to 1 unit up from the xy plane. Here's a picture showing you, here's a picture showing you that this is not such a crazy concept. If I have this elliptic oval region in the xy plane and I want to compute its area, well, the volume formula for this figure tells you that the volume of the whole shape is the base area times the height. And if we choose the height to be 1, then the volume as a 3-dimensional measurement is 1 times the base area, or just equal to the area in square units. So just numerically, we can recover areas by computing volumes with respect to the function, the height function z equals 1, or f of xy equals 1. It's a technique that we'll see in one problem on the classwork, but it gives you an alternative for computing things like the area between two curves or the area of some more difficult region if you're able to parameterize and write out double integrals for regions like this. Here's some summaries for this video, and then I'll turn you loose on some more double integral problems for you to practice on. First of all, what are the steps for writing a double integral over a general region that's not necessarily a rectangle? Next, how do you decide whether dx or dy is the inner variable to integrate first? What is antisymmetry and how can we use it to evaluate integrals? And finally, how can we use a double integral to compute the area of a region in the xy plane? That's it for now. I'll see you in class to practice with more of these, but there are lots and lots of practice problems out there that you can do on your own. So thanks for tuning in.